The recent images of 3 Atlas have pushed the situation into a genuine emergency, prompting the United Nations to activate a planetary defense mission unlike any previously used for an interstellar object. New observations show a tail stretching nearly 5 million kilometers and an anti-tail rising toward the sun, forming a display that defies everything normally expected from a natural comet. These formations appear bright and stable, and their sheer scale implies a force far stronger than ordinary ice-driven activity. With the UN now involved, the question expands further. If this is only the start, what will future measurements uncover? The activation of the United Nations Planetary Defense Exercise represents a major shift, signaling that 3 Atlas is no longer just a curious object in the sky. The International Asteroid Warning Network announced an intensive observation campaign scheduled from late November 2025 through January 2026. This kind of timetable is typically reserved for objects considered serious threats that demand constant monitoring. This marks the first time an interstellar visitor has been chosen for such an exercise, and the decision immediately raised questions about what the agencies anticipate discovering. The network explained that comets complicate measurements because their glowing comas can distort the apparent position of the nucleus, making orbital calculations unreliable without continuous data collection. While this reasoning sounds logical, it does not fully justify the need for a full planetary defense exercise. The official stance is that the campaign offers a valuable opportunity to train using real data from a fast-moving visitor. However, many observers noticed a cautious tone in the agency's statements. When the Minor Planet Center released its report, several passages emphasized the need for as many telescopes as possible to monitor every change in brightness and trajectory. This level of scrutiny is unusual for a standard comet. NASA reiterated that Atlas poses no threat to Earth, yet its language focused more on reassurance than on detailed explanation. The European Space Agency added that the exercise would enhance cooperation among observatories, a statement that sounded more diplomatic than scientific. Together, these carefully worded messages created the impression that something remains unresolved. Attention was also drawn by the network's own history. Since 2017, it has conducted only 8 official exercises, each involving asteroids that pass close to Earth or carried a small chance of impact. Atlas does not belong in that category, as its closest approach lies far beyond any real danger. Even so, the network behaved as if preparing for a real-time test, suggesting a desire to fully understand the object while keeping the public calm. Several astronomers pointed out that Atlas's rapid motion makes it difficult to model, which alone could justify increased monitoring. Still, the timing of the decision feels unusual. Perhaps most striking is how the announcement avoided mentioning the strange behavior reported for months by private researchers and independent astronomers. Instead of addressing unexplained patterns in the tail and anti-tail, the agencies focused on general comments about data quality. This reluctance to acknowledge the anomalies led many to suspect that the campaign is not merely a training exercise, but a way to collect high-resolution data without causing alarm. Because interstellar objects cannot be reliably predicted using long-term models, agencies may worry that Atlas could behave in ways that challenge established theories. As the exercise begins, the central question remains, why activate it now? If nothing is unusual, why commit so many resources to an object deemed harmless? This is where the story becomes even more significant, because new images captured by independent astronomers reveal details the agencies have not addressed. What did those images show that shifted the tone of the entire investigation? Images taken by independent astronomers quickly became the focus of attention after revealing features absent from official discussions, raising doubts about the subdued tone used by NASA and the European Space Agency. The most remarkable image came from Mitsunori Sumiura, who used a half-meter telescope to capture a tail nearly 5 million kilometers long and an anti-tail extending toward the sun. The length alone was striking, but the clarity and stability of the structure made it even more unusual. Rather than displaying the broad, diffuse shape common to many comets. The tail appeared as a narrow line that maintained its form over an immense distance. Samura's image was soon compared with additional photographs from Peter Carson Law and another observer named Walter, all showing the same pattern. These images drew attention partly because they appeared sharper than those released by NASA, leading many to wonder why amateur astronomers produce clearer results than agencies with vastly superior equipment. While the agencies explained that their instruments required longer exposure times, observers noted that the independent images were consistent and revealed structural details that could not be dismissed. Most intriguing was the anti-tail, which appeared as a bright, narrow column extending more than 1 million kilometers and pointing directly toward the sun, contradicting expectations for dust behavior under solar radiation. Instead of curving away, the column remained straight, as if constrained by an unknown force. The consistency across multiple observers indicated that the structure was not a product of equipment limitations or image processing. It suggested an internal pattern within 3 Atlas that allowed jets to form a stable geometry. This raised questions about whether the object responds to sunlight in a simple manner or operates under more complex conditions. Typically, a comet shedding material at high speed produces chaotic trails that shift with solar wind pressure. Yet these images showed clean, sharp lines that persisted as the object moved through space. Some viewers likened the appearance to a system with controlled flow. While speculative, the contrast between Atlas and ordinary comets was difficult to ignore. The brightness of the coma also drew interest, as it remained uniform despite the object's rapid motion. A typical coma shows uneven regions where ice sublimates at different rates, but Atlas displayed a smooth glow with no visible breaks. This suggested the material source might originate from deeper layers rather than random surface pockets, implying an internal process not yet fully understood. Even astronomers who consider the object natural admitted that the images revealed something highly unusual, as the structures behaved like organized streams rather than scattered dust. As the images circulated online, debate intensified, fueled by the contrast between official statements and independent observations. This gap became a major reason the public began searching for deeper explanations. If such precise structures persist, what will future measurements reveal about the true nature of 3 Atlas? The 12th anomaly identified by Professor Avi Loeb became one of the most puzzling clues, focusing on the rotation of 3 Atlas and the behavior of its long jets. The concept is simple but difficult to reconcile. If the object rotates every 16 hours, the jets should display clear signs of motion. A rotating body releases material in curved patterns that stretch into spirals over long distances. Atlas's jets extend more than 1 million kilometers, and across such distances they should appear twisted or blurred. Instead, new images show straight streams with sharp edges, a contrast that cannot be ignored. Researchers expected some distortion, since sunlight heats different surface regions at different times, usually producing uneven flows. The persistence of narrow, stable jets suggests the rotation may not align with earlier measurements. Loeb proposed that the object may have slowed since the summer, but this idea conflicts with typical comet behavior. Outgassing usually increases rotational speed, creating stronger curvature in jets. A sudden slowdown would require a force counteracting rotation, and no simple natural mechanism explains such change. The behavior appears irregular compared to the predictable patterns seen in other objects. Another possibility is that the jets are not continuous but erupt in short bursts from specific surface locations. Loeb described a scenario in which deep valleys trap ice that receives sunlight only at certain angles, producing focused streams during brief moments of illumination. This could explain the straight jets, but it also raises questions about Atlas's internal structure. If the surface supports such controlled flows, the object may be more solid or organized than the loose, fragile bodies usually associated with interstellar space. A comet composed of soft material would not normally maintain such steady channels. The situation becomes even stranger when considering jet length. Material extending over 1,000,000 km must leave the surface at high speed, which should reveal any rotational motion. Even slow rotation should cause slight bending, yet the images show nearly perfect lines. This has led some to compare the jets to controlled exhaust rather than natural gas release. While speculative, the resemblance has driven many to seek deeper explanations. As astronomers continue examining the anomaly, the broader question grows more significant. Rotation influences every aspect of the object's behavior. If Atlas is not spinning as expected, what does that imply for its other characteristics? This becomes even more critical when considering the next strange feature, how the anti-tail moves through the solar wind. Could the rotation mystery be the first sign that Atlas operates under conditions outside natural models? The strength of the material streaming from 3 Atlas emerged as another major surprise, as the anti-tail pushed directly against the solar wind, astonishing many astronomers. The solar wind travels at roughly 400 kilometers per second and typically forces dust and gas away from comets. Yet Atlas displayed a column that remained intact under that pressure. A structure that stays stable in such conditions must carry substantial mass, prompting Professor Avi Loeb to estimate how much material Atlas has lost. His calculations suggest several billion tons have escaped the surface over the past 2 months, a figure that raised further questions. Natural comets lose mass through sublimation, but the amount depends on exposed surface area. Hubble data indicates Atlas's nucleus is far too small to produce the observed output through normal processes. If the surface area is insufficient, gas cannot be generated at the required rate, and the anti-tail should be far weaker. Instead, observations show a dusting gas column maintaining its form across distances exceeding 1,000,000 kilometers. This mismatch between expectation and observation has forced researchers to reconsider what processes might be active within the object. Loeb noted that a technological thruster could generate similar acceleration with much less mass loss, as controlled exhaust travels faster than sublimated gas. This idea remains speculative, but it highlights the difficulty of explaining the anti-tail using only natural mechanisms. Since the solar wind is a continuous stream of charged particles, any natural plume should bend or disperse. Yet Atlas consistently produces a column pointing the opposite way. Such behavior implies that the forces involved may differ from those experienced by typical comets, deepening the mystery. Another possibility is that the material leaving the surface is denser than expected, allowing heavier particles to resist the solar wind more effectively. However, this raises new questions as spectroscopic data so far shows no evidence of unusually heavy elements. Without such proof, the explanation remains incomplete. There is also the possibility that Atlas's internal temperature is higher than predicted, enabling deeper layers to drive powerful flows. But astronomers have not found thermal data to support this idea. Each potential explanation introduces another missing piece, and the puzzle grows more complex as new images emerge. The next step is to obtain detailed spectroscopic measurements, which could reveal chemical properties and clarify how the anti-tail sustains its strength. If the data shows the gas behaves like ordinary comet material, the mystery will deepen further. This leads to the next critical moment in the story. Since an encounter with Jupiter could expose clues invisible from Earth, what will Atlas reveal as it approaches the region dominated by Jupiter's gravity? The upcoming encounter between 3 Atlas and Jupiter has become one of the most anticipated phases of the investigation, as it may reveal behaviors impossible to observe from Earth. Jupiter's gravity governs a vast area known as the Hill radius. Within this zone, objects can remain bound to Jupiter rather than being pulled away by the Sun. Atlas is expected to pass directly into this boundary on March 16, 2026, prompting researchers to question whether the timing is coincidental or part of a meaningful pattern. Professor Avi Loeb noted that the precise distance at which Atlas will cross the hill radius heightens the event's importance. If the object releases material or fragments inside this region, those pieces could remain trapped in Jupiter's orbit instead of drifting back into deep space. This raises the possibility that Atlas contains smaller components that might behave differently once separated. Since Jupiter's gravity acts as a natural trap, the encounter offers a rare opportunity to detect unusual activity that would otherwise be difficult to observe. NASA plans to use the Juno spacecraft to monitor radio waves during the encounter, scanning frequencies from 50 Hz to 40 MHz. These signals could reveal electrical activity or patterns suggesting controlled processes within the object. While such signals alone would not confirm anything unusual, they would justify further investigation. The European Space Agency has also shown interest, with its JUICE mission having already conducted early observations of Atlas. However, the data will not reach Earth until early 2026 due to slow transmission speeds. This delay has heightened curiosity, especially among those tracking Atlas's behavior for months.